Hello and welcome to Rails tutorial. Today's topic would be on inclined plane. This is the last subtopic on force and translational dynamic. So far on translational dynamic, we have looked at the following subtopics. We have looked at Newton's law of motion, weight and normal force, friction, pulling. Now we are going to focus on inclined plane. A link of the translational dynamics playlist will be attached up, so you can watch the YouTube link to recap. Okay.
Before we proceed with today's lesson, some people have asked me for reference textbook. So far, I've prepared this tutorial using AP Physics 1 Premium Prep and Physics for Dummy Book 1 and 2. I will add this textbook link to the description below so you can order them. Okay, now let's continue with the lesson.
First, what's an inclined plane? An inclined plane is also known as a ramp. So let's draw a ramp. The ramp of a car is an inclined shape. An inclined plane can be drawn in that form. It's like a car ramp. It often has a higher and a lower end, which is used to either raise or lower an object. So this is an inclined plane. This is the higher side of the inclined plane. This is the lower part of the inclined plane. And here is an object. From this description up above, it says an inclined plane is also known as a ramp. It's a flat supporting surface tilted at an angle from the vertical direction, with one end higher than the other, used as an aid to raise or lower a load. However, part of the inclined plane can also be described as, if you look at the force acting on a block seated on the ramp, this ramp, using a standard coordinate. It's using a standard coordinate. So we have, this is a block here, and let's have a standard coordinate. When we say a coordinate, that is the X and the Y coordinate. This is the X and this is the Y. That's the X and the Y coordinate. So when we have a block on this, this is the standard coordinate as the X and the Y coordinate. It usually looks direct when it's applying the X and the Y coordinate. It looks direct. However, the part of the force, the normal force is a force that is usually perpendicular to the object or the surface. But now we're talking at an inclined plane. In this part, the normal force, let me draw this inclined plane further here. We have, here is the object. Then we have the coordinates. For this object, the normal force of the object is here. This is the Fn. That's the normal force of the object, which is between the X and the Y direction. This is the X, and here is the Y. And the normal force is in between the X and the Y direction. And the block is also, since the block here, there's an acceleration that's pulling this block, and the block is also accelerating along the same X and Y direction. That is the block. So when we have a block on a ramp, it has a normal force applied on it. It also has a frictional force of weight, that is the force of gravity, then it has its acceleration. But in this case now, when the friction is applied onto this, the frictional force applied onto this is the object, and here's the friction, F of n applied here. Now the friction is also in between the x and the y axis. So for us to determine how the normal force is, would be on the ramp in an inclined plane, we go through this process called coordinate system. So in an inclined plane, we can either have two coordinate system. It's either a non-rotational rotated coordinate or rotated coordinate. Let me explain further on the next slide. So as I was saying earlier, we have a non-rotated coordinate system and a rotated coordinate system. In the non-rotated coordinate system, draw this again. This is a plane. In the non-rotated system, here is a plane and here is the object. In this case, the frictional force, the normal force, and the acceleration are each broken on the x and y coordinates. Now let's look at this. Here is the coordinates. Here is the coordinate. Here is the x and here is the y. The normal force on this object falls between the normal force here, that is the F of n as the normal force, and the object. Always remember that the force of gravity is always perpendicular to the object, that is Fw. Then we have the force of friction. The force of friction applied on this object is also between the x and the y coordinate, is the F of x, F of f. Then we have the acceleration. Acceleration applies this way. That's the A. So now if you look at this graph, the force of normal force in a non-rotational coordinate, it's not rotational. The force of friction, frictional force, the normal force, and the acceleration will each be broken into the x and y coordinates. So let's look at this. The normal force is between the x and the y coordinate. The frictional force is between the x and the y coordinate. Acceleration is between the x and the y coordinate. Then we have a non-rotated coordinate system of an inclined plane when a friction is applied. That's how that is being defined. So in this case, this is a non-rotated coordinate system. Let me draw it on a straight graph like this. Let's assume here is the object on the ramp. So here would be, just for more clarification, here is the F of n, normal force. This would be the force of the weight, force of gravity. Here would be frictional force, F of f. And here is acceleration, A. So if you look at them all, they are all in between the x and y components direction, x and y direction. All right. So now let's look at rotated coordinate system. In rotated coordinate system, the frictional force and acceleration are parallel to the ramp, while the normal force is perpendicular to the ramp. And the force of gravity is to mg, that's mass times gravity. And let me draw that diagram. Let's draw a ramp. And here is the object. Here is the coordinates. As defined here, the normal force is perpendicular to the ramp. So if this is the normal force, it's perpendicular to the ramp. So here is F of n. The frictional force, this is the force of friction here, is parallel to the ramp. So is it parallel to the ramp? Here's the force of friction, goes this way, F of F. And also the acceleration too is parallel to the ramp. There is A, acceleration. But the force of gravity is always perpendicular to the object. So this is F, W here. That's how it's been laid. So if an object of mass m here is on the ramp, then the force of gravity on the object Fw is equals to mass times gravity, mg. So this mass times gravity, it has two components. Let me draw this again. It's an object on the mass. Then the mg, since this is the x and the y axis, and here is the mg. So for us to get this mg, it will be, there'll be two components. One component would be run down this way. This is one component. And this will be the mg. This will be the mg cos theta. But by the second component here will be the mg sine theta. Mg sine theta. So one of these components will be parallel to the ramp, and that will be the mg sine theta. And the one that is normal to the ramp will be the cos, mg cos theta. So this is normal, mg cos theta is normal to the ramp. The ramp is, since the normal force is perpendicular to the ramp, and the mg cos theta is perpendicular to the ramp, so it is normal to the ramp. Whereby the one that is parallel to the ramp will be this will be parallel to the ramp, mg sine theta, and the mg cos theta is perpendicular to the ramp. The force driving the block down the inclined plane is a component of the block's weight. The block's weight, this weight of this block here, the weight of the block here, that is parallel to the ramp. And that's the force driving this weight of the block that is parallel to the ground is the mg sine theta. That is this one, mg sine theta. Because that is the one that is parallel to the block. Okay. So for clear understanding, the rotated coordinate system, the normal force is perpendicular to the ramp. The frictional force and the accelerations are parallel to the ramp. And the force of gravity on the object is Wm is equals to mg. And the mg has to coordinate, that is force of the weight has to coordinate. We have the mg cos theta, and we also have the mg sine theta. the mg sin theta is parallel to the object or to the ramp, whereby the mg cos theta is perpendicular to the ramp, which is same thing as the force of normal, same thing as the normal force. Okay. Let's, based on what we explained before, a more clearer definition of this. Looking at this image here, the force can either be static or frictional. So in this first diagram here, this is a static friction. Starting up from here, the normal force, like we mentioned, it's always perpendicular to the ramp when it's in that form. So it's perpendicular to the ramp. Then we have the force of the weight. So this angle here defines the force of the weight. Then we have the mg cos theta, that is parallel to, is equals to the same as the, is equals to the normal force, and the mg sin theta is parallel to the ramp. So in this case, the coefficient of static friction will be tan theta, because we have normal force f of n is equals to normal force, f of s is equals to static friction, fk is equals to kinetic friction. Now looking at kinetic friction here, definition as static friction, but the difference now is we have acceleration has been applied to this curve. This kinetic friction, the friction is in motion. Static friction is when it's a stored friction, there's no motion. Now here there's a motion, and the normal force is still perpendicular to the ramp, and we have the mg is parallel to the ramp. The mass of mg cos theta is perpendicular to the normal force. So mg cos theta is equals to same thing as mg cos theta is same thing as the normal force, and the mg sin theta is one parallel to the ramp. So in this case, we have the mu k, that is the coefficient of kinetic friction, is equals to gravity sin theta minus a over g cos theta, whereby g is gravity, sin theta is the angle, a is acceleration, and all. I'm going to explain this further with more examples. But let's just always remember that rotated coordinate system is when the normal force perpendicular to the ramp. The non-rotated coordinate system is when the normal force is between the x and the y direction. Okay. Let's look at some examples. A block slide from a frictionless inclined plane that has an angle of 30 degrees with the horizontal. Find the acceleration. Let's draw an angle. Let's draw a block here. A block slide down from a frictionless inclined plane. So this is an inclined plane on a block which is frictionless. And at an angle of this, so right now the weight is what we have here. So this is frictionless. We have the force of the weight here. So we're looking for the acceleration. What is the acceleration? So this is frictionless, so it's just going to be, we're looking at the angle that is parallel to the ramp. And as we mentioned earlier, we have this angle and we have this angle. This one will be the mg cos theta. And this angle, this side of the angle will be the mg sin theta. Okay, so since we're looking at it's frictionless, in that form, we're looking at the one that is in parallel, how the object moves, the acceleration of the object. This is our focus, the mg sin theta. Then for us to find the acceleration, and we know that for us to find acceleration, A is equals to force over the mass. Now, which is equals to, the force now is this mg sine theta over m. But to break it easily down, let's cross out all the m's. This m cancels this m. Then we have a is equals to g sine theta. For further explanation, substitute the values of each of that. So therefore, a is equals to g sine 30 degree. And sine 30 is equals to half. So a is equals to half g, which is equals to, and we know g is 10, that is 1 over 2 times 10 meters per second square, which is equals to, answer would be, the answer is equals to 5 meters per second square. Okay, so that is the answer. Right. Let's look. We asked to find the acceleration of the block, and the acceleration of the block is 5 meters per second square. Okay. Now let's look at this example. A block is sliding down an inclined plane that makes an angle of 30 degrees with the horizontal. If the coefficient of friction is 0.3, find the acceleration of the block. Let's draw that inclined plane. Right now, this is the inclined angle. This is the block here. It says it's a friction applied. So the friction applied this way. This will be the F of F, frictional force. Acceleration. Then we have the normal force here, the F W, which is equals to, we have the F W cos theta, right? Now we're looking for the acceleration. So for us to find the acceleration will be the F to be A minus F of F, which is equals to, and the A, since the A is parallel to the ramp, I was told initially that the normal force that's parallel to the ramp is equals to mg sine theta. So we change this now to be, A will be mg sine theta minus fx, right? Now we know that f of x is equals to mu, and we know that what? Coefficient of the frictional force. We have it here now. That this is the diagram that we are looking at, the focus diagram. So now we know that mg sine theta minus mu, because of this will be f of n. Since f of n is the same thing as fw cos theta, so we have it here as mg sine theta minus mu mg cos theta, which is the same thing as what? Mg theta sine theta minus mu cos theta brackets. So that we now have this as that value. Well, I'll know acceleration A is equals to force over mass. Now, all of this applies as a force, right? So we'll have it as mg bracket sine theta minus mu cos theta all over m. So this m cancels out. M cancels out. And that leaves us to have just, which is equals to A B G bracket sine theta. Just the sine theta. That will be sine theta is what? That is sine theta will be what then? Sine 30. Theta is 30. Then 30 degree minus mu cos 30 degree. Okay. And here we know that G is equals to what? 10. So 10, by the time we calculate all this together, A would be equals to 2.4 meters per second square. Okay, so that's the answer of the acceleration. So the acceleration on the block is 2.4 meters per second square. All right, this is the end of today's topic on translational dynamic at this incline plane. I'm going to add the link of the previous and the playlist for the translational dynamic up here so that you can review and watch that to recall what we did during translational dynamic, and that was Newton's law of motion. What else again did we do? We did Newton's law of motion, we did pulling, we did weight and normal force, and we did friction. Okay, so until the next lesson, probably the next lesson we're just going to solve different exam questions on AP Physics, and that will help us refresh what we practiced in the two last classes, kinematic, force and translational dynamics. All right, please do not forget to subscribe to this YouTube channel. Please like, comment, and subscribe to this YouTube channel. Until the next class, see you. Bye.